Okay, friends, in our last class we have seen how to obtain the end moments of the continuous beam, the problem which is shown over here. Now in the free body diagram, whatever end moments that we had calculated, for example MAB is 51.34, which is in counterclockwise direction, is shown over here. Similarly MBA is in clockwise direction, which is shown in clockwise. Then MBC, MCB is shown for the second span, MCD, MDC is shown for the third span. Now we also need to calculate along with end moments, we have to calculate end shears. So these shear forces can be calculated by considering the equilibrium of the individual span of the beam. That will see simple moment equilibrium equation, and the force equilibrium equation will give you the end shears. So in this slide we have I have taken the first span where the all the required end moments and the external load along with the unknown end shears are shown. For example, for span AB, the end moments are 51 in the counterclockwise direction, 95 in the clockwise direction. The loading is also shown over here in AB, and SAB and SBA is considered as your end shears. Now considering this free body diagram, we have to consider the equilibrium of the moment acting about B. All moments acting about B considering 0. Then writing moment equilibrium equation and solving it, you will get SAB. Now remember to include all the moments, that is this moment and the loading, moment due to loading as well as moment due to this end shear. And the remaining value of SBE, BA will be obtained by considering this equilibrium equation. This is a force, vertical force equilibrium equation, summation of these two reactions as well as the load, whatever vertical loads and vertical reactions that are acting, we have to include in this equilibrium equation, and in the process we are getting SBA. The similar approach is followed for the remaining spans, and we are getting the end shears for span BC as well as for span CD. You can check it yourself by calculation that you are getting values of the end shear. Now to calculate the support reactions, actually it is nothing but the vertical reaction at support B is obtained by adding the summation of shear forces at that particular support SBA and SBC. So when we add these two end shears, we are actually going to get the support reactions, ruler support reactions at B. And similarly we can obtain at support C what are end shears at support C, SCB and SCD, CB coming from span CB and CD coming from span CD is being added to get the reaction at support C. Now to get bending moment and shear force diagram, how to plot, it's not that difficult. You have to follow the conventional sign of bending moment and the shear force. For example, the left side upward and right side downward is considered as positive shear, and left side downward and right side upward considered as negative shear. Now you can just check the free bodies diagrams which I have shown earlier. The arrows going from the left in vertical direction gives you positive shear. So you can mark this positive shear area, and on the right hand side the arrows going upward is giving you negative shear. So obviously for this UDL, the shear force is simply basically this kind of triangle, and there will be a point where point of zero shear, that we will discuss later on how to get this point. Now in the second one you can see the positive shear gives you 72.46, and of course there is a concentrated load, so there will be a constant, there is no load in between, so this will be the constant. After this loading there will be decrease in the shear force, or else you can simply mark from the right upward direction gives you negative shear force, and the value is minus 62.54. And in the next line it gives you upward positive shear, there is no load in between, and it remains constant and till the end, and it gives you negative shear at the end, so it becomes 0. Now to plot the bending moment diagram, again you can mark the, according to our sign convention, positive tension in the bottom fiber, compression in the top fibers, and opposite is negative. You can mark the negative bending moments, and by simple judgment you know the UDL, it gives you parabolic. For concentrated load it gives you triangle, and if there is no load here you can simply mark according to our sign conventions which you have followed. For example, at the last you are having for last one you are having anti-clockwise moment, it gives you positive value here like this. Now how to obtain maximum point of bending, where maximum bending moment will occur, point of contraflexure where the bending moment changes its signs. That can be determined easily by considering this simply free body diagram of the first one. You can you want to know the maximum bending moment, you can first write the bending moment equation at any distance x. Take the differentiation of this moment is equal to 0, gives you the value of x where exactly the maximum bending moment will occur. So here you are getting 2.67. This is extra because prior to your strength of material knowledge you can easily calculate this, and you can explore later on your own, and you substitute this value of x in the bending moment equation, you are likely to get 27, and that is roughly the same which I have shown in the bending moment diagram. So you have to mark actually, and this point of contrafracture, actually this is zero shear force where maximum bending moment will occur. Now in the next second one, you can see here the bending moment which is for the second one the free body diagram is shown at any distance x from the right side of the concentrated load. You can just write the bending moment equation, and since this is a symmetric case, the concentrated load is acting at the center, you can simply substitute the value of x and get the value of moment. Now for the last one, you can again calculate the point of zero moment. So you write the bending moment x1 by drawing the free body diagram, by consider at any distance x, write the moment equation, and then make the moment 0, because we are going to calculate moment is equal to 0, and from this you are going to get x equal to 3. You can substitute x and where the bending moment gives you 0.